is your video for 8.1, integral as a net change. So this is really going to start our applications of integrals. That's what this entire chapter is about. So this first one, this first section really deals with accumulation. So things that are accumulating over a set amount of time. So figure 8.1, that's in your textbook, is going to show the velocity, ds dt, which is the same as velocity, is t squared minus 8 over t plus 1 to the second power of a particle moving along the horizontal s-axis for t is in between 0 and 5, and we need to describe the motion. So your motion, we have that particle has our initial velocity. So if t is equal to 0, our velocity is going to equal -8. So this particle has an initial velocity of -8, and this is meters per second using the units that are given in the problem. So that means that it is moving to the left. So initially this particle is moving to the left. If we set this equal to 0 and solve, it's going to stop at t equals 1.25 seconds. Because again, that's where the velocity is equal to 0. Then it is going to move to the right with increasing speed, and eventually your ending velocity, if we plug in a 5 there, that's approximately equal to 24.8 meters per second. Let me just double check that unit there, because it looks like I have both centimeters and meters written into my notes. And it should be centimeters. It is centimeters, not meters. So that's centimeters. This one up here is also centimeters. So it's going to stop at 24.8 centimeters. Well, not going to stop, but when the 5 seconds are up, that's going to be your 24.8 centimeters per second. So that is the movement, the motion of the particle when we describe that. So example 2, it says, suppose the initial position of the particle is 9. So we're starting at 9. We want to know what the particle's position is at 1 second and at 5 seconds. So our displacement is equal to, for part A, the integral from 0 to 1 of v of t dt. So I want to know how far the particle moves over the first second, and then I'm going to use that 9 to incorporate to actually figure out what my final position is going to be. So the integral from 0 to 1 of my function t squared minus 8 over, and I'm actually going to rewrite this a little bit. Instead of 8 over t plus 1 squared, I'm going to say minus 8 times t plus 1 to the -2. And then that's dt. So if I do the antiderivative there, I get 1/3 t to the 3rd. With this one, I'm going to add 1 to the exponent, so it's going to be to the -1, and then I divide by the new exponent, so it's going to be plus 8 times t plus 1 to the -1 power. And then we're evaluating that whole thing from 0 to 1. So I have to plug in the 1 and plug in the 0. Well, when I plug in the 1, I'm going to get 1/3 times 1 cubed plus 8 times 1 plus 1 to the negative 1 power. And then I subtract when I plug in the 0. So 1/3 times 0 to the 3rd power. And again, this is using that fundamental theorem. So 1/3 plus 8 times 1 plus 1 to the negative 1. Well, 1 plus 1 is 2 to the negative 1 means this is going to be 8 over 2. So this is going to be 1/3 plus 4. Over here, this is 0. 1 to the negative 1 power is still 1. So 8 divided by 1 is 8. So I have 1/3 plus 4 minus 8, which is going to give me negative 11/3. So this is the displacement over that first second. However, we were starting at 9. So our position is going to be 9 minus 11/3. Which is 16/3 centimeters. So if we're starting at 9, at the end of 1 second, my new position is going to be 16/3. For part B, and I believe I'm going to do that on the same page. Yeah, we're going to do that on the same page. We just might need a little bit more space. Part B is going to be the same thing, except now my integral is going from 0 to 5 of the t squared minus 8 times t plus 1 to the negative 2. I already know what I'm going to get. I'm going to get the 1/3 t to the 3rd plus 8 times t plus 1 to the negative 1. And then this is evaluated from 0 to 5. So really, I just have to plug in the 5. I already know I'm going to get minus 8 whenever I plug in the 0. So this is going to be 1/3 times 5 cubed plus 8 times 5 plus 1 to the negative 1 power. And then minus 8, because I'm going to get the same thing when I plug in 0 for part A as when I plug in 0 in part B. So when we simplify everything that is in the parentheses, you end up getting 43. So my total displacement, or my displacement, is 35 centimeters. So my position is going to be 9 plus that 35, which is 44 centimeters. So after 1 second, I'm at 16/3 centimeters. At 5 seconds, I'm at 44 centimeters. In addition to displacement and position, the last thing we can look at is the total distance traveled by your particle. So total distance would be, it doesn't matter if you're moving in the negative or positive direction, you're looking at just the total movement. So even though, let's say you move 2 to the left and then you move 2 to the right, your position is going to be exactly where you started, but your distance traveled is 4, because you traveled 4 there and 4 back. It doesn't necessarily matter where you end up exactly, but it does matter the area that you covered. So in order to do this, because it says total distance, we are looking at the absolute value of the velocity. Because when you have absolute value, it doesn't matter if you have a negative movement, everything gets flipped above the x-axis, so everything is going to be positive. This is going to be something where you want to use your numerical derivative. So here's how this is going to look set up. And I'm going to go ahead and set this up like this because I will be using the calculator to go through and solve this. So here's my calculator. I know this might look a little different than what you've seen before. Since I switched computers, I had to download a new calculator. However, make sure you just pay attention to the screen over on the right-hand side. That's the bigger version of the calculator main screen. We're not really going to be using the other 3 screens for this one. So you want to press the math key, and option number 9 is going to be your integral. If you have one of the older black calculators, I'll write on the smartboard what you would need to do in order to be able to use that, because you do have to do a little bit of kind of programming to figure that out. So I'm going to put the 0 in the bottom, the 5 in the top, and then just like I wrote out my integral, this is where I would put in my function, but I need to go math over to NUM and select number 1 with absolute value, because I have to take the absolute value of, and the t's are actually going to change to x's here. So we have x squared minus 8 divided by parenthesis x plus 1 squared. Then I need to put in my constant of, or my variable of integration, which is going to be my x. Hit enter. It does a little bit of thinking, and you can see 42.587 is going to be our final answer here. So 42.587 centimeters is going to be the total distance traveled. So again, if you have those black calculators, those older TI-83 pluses, you would have to, again, select that FN int. It's going to open up a parenthesis. Then you type in the absolute value of t squared minus 8 over t plus 1 squared. And you'll probably not see the bars. You'll actually probably see an ABS and a parenthesis instead of the bars there. So after you close the absolute value, you're going to put a parenthesis. Then you're going to put your variable of integration, which actually, instead of t's here, you would actually probably want to put x's in there for that. So then you put an x, then you put the lower bound, which is 0, with a comma, and then the higher bound, which is 5. Close your parenthesis, and that should give you the same answer that we got with the other one. If that doesn't work out for you, please contact me and we can do some calculator troubleshooting. So here's your strategy for modeling with integrals. You want to approximate what you want to find a Riemann sum of values with your continuous function multiplied by interval lengths. So that's basically, you want to think about it as a Riemann, but really you want to write your definite integral to express the limit of your sums as it says the norms of the partitions go to 0. So basically, as those slices get thinner and thinner and thinner, we are going to get more and more accurate and closer to the actual value. And then finally, evaluate your integral numerically or with some type of antiderivative. Before I end this video, I am going to do actually, with that phone ringing there, I'm going to go ahead and stop this. So go ahead, go back and rewatch this, watch part 2, contact me if you have questions.